When you think about it, the world of cameras, telescopes, even your own eyeglasses, it all seems incredibly complex, right? But what if I told you it all boils down to a few surprisingly simple and honestly really elegant rules of physics? Well, today, we're going to crack open that rulebook and take a look at the math that literally makes our world visible.
So here's our game plan. First, we're going to lay down the law, a universal rulebook for how we talk about light. Then, we'll bust out the formula toolkit that lets us make some amazing predictions. After that, we'll figure out how to size up an image. And to wrap it all up, we'll uncover what that power number on your glasses prescription actually means.
Okay, first things first. Before we can even start to calculate anything, we all need to be on the same page. We need a map. Think of it like a GPS for light rays. It's a universal coordinate system, so that when I say left, you know exactly what I mean.
And these are the rules of the road. It's called the new Cartesian sign convention. It's super simple. Everything, and I mean everything, starts from the center of the mirror or lens. We call that the pole. Rule number 1, we always put the object on the left. Rule 2, all our measurements start from that pole. This means any distance to the left is negative and any distance to the right is positive. And finally, anything above that center line is positive, anything below is negative. That's it. That's the whole framework.
And here's what that looks like in action. See that P? That's our origin, our 0 point. Now, since the object is always on the left, the light is traveling from left to right. That means the object distance, which we call u, is measured to the left of P. So u is always going to be a negative number. Seriously, getting the sign convention right from the start is the key to everything else we're about to do.
So now that we have our GPS, we can grab the tools that actually let us predict the future, or at least the future path of light rays. Let's open up the formula toolkit and see how we can figure out exactly where an image is going to show up.
And this is where physics just gets so cool and elegant. Just look at these two formulas. One for mirrors on the left, one for lenses on the right. They are almost identical. The only difference is that tiny little plus or minus sign. And that all comes down to whether light is bouncing off something, reflection, or bending through it, refraction. It's amazing.
So what do all those letters mean? It's pretty straightforward. U is just how far the object is from the pole. V is how far the image is from the pole. And F is something called the focal length of the mirror or lens. These three little variables, they tell us the whole story.
Okay, so knowing where an image is going to pop up is great, but that's really only half the story, isn't it? The next big question is, what's that image going to look like? Is it going to be bigger, smaller, right side up, or upside down? To answer all of those questions, we use one simple concept, magnification. We just call it M. It's basically just a ratio, the height of the image divided by the height of the original object. But this one little number packs a ton of information.
And here's a fantastic shortcut. If you do the math and your magnification M turns out to be a negative number, you instantly know two things about your image. First, it's real, which means light rays are actually meeting at that spot. You could put a screen there and project the image, just like at the movies. And second, it's inverted, which is just a fancy way of saying it's upside down.
And, you guessed it, the opposite is just as simple. If that magnification number is positive, your image is virtual. The light rays only look like they're coming from that spot. You can see it, like your reflection in the bathroom mirror, but you can't project it onto a wall. And it's erect, meaning it's right side up. So the sign, positive or negative, that's the magic key. It tells you everything you need to know about the image's orientation.
All right, let's head into our final section and bring all this together. We're going to connect all these rules and formulas to something you might have seen before, maybe even something you carry around with you every single day.
We are talking about the power of a lens. And it's not some vague term. It's a very specific measurement of how strongly a lens can bend light. A high-power lens gives light a really sharp bend, while a low-power lens gives it just a gentle nudge.
Does this look familiar? I'm willing to bet you've seen a number just like this on an eyeglass prescription, a number that has a huge impact on how someone sees the world around them.
But what is it really telling us? What is that plus 2.0 and that kind of mysterious letter D actually describing about that piece of plastic or glass that you put in front of your eyes?
Okay, mystery solved. That D stands for diopter. It's the standard official unit for measuring the power of a lens. And the definition is super simple. 1 diopter is the power of a lens that has a focal length of exactly 1 meter.
And that little plus or minus sign in front of the number, that's absolutely critical. A positive power, like in our example, always means you're dealing with a convex lens, the kind that bulges out and brings light rays together.
A negative power means it's a concave lens, the kind that curves inward and spreads light rays out.
And here it is, the beautifully simple formula that ties it all together. The power, P, is just 1 divided by the focal length, F. As long as F is in meters, that's it. So a plus 2.0D lens, that just means it has a focal length of ½ a meter, simple as that.
So why do we even use power, instead of just talking about focal length? Well, as the source material points out, it's all about convenience, especially for opticians. See, if they need to combine lenses, they can just add the powers together. A +2 diopter lens plus a +0.25 diopter lens gives you a +2.25 diopter system. It's just elegant and super practical.
So there you have it. We started with a simple set of rules for direction, and from there, we've unlocked the formulas that run everything from your glasses to the Hubble Space Telescope. Every camera, every microscope, it's all just a combination of these basic principles. You now have the fundamental toolkit. Kinda makes you wonder, what else could you build with it?